And go for the last speaker of the session, that is Aitor Villafranca, postdoctoral researcher of CSIC and founder of Alcyon Photonics, who is here to present polarization and mode handling building blocks on chip.
How do I show it over there? Oh, there you go. So thanks for the introduction, and thanks a lot for the invitation to be here. This title slide is a bit crowded, but that's because everything that I'm going to show is a collaborative work. All the devices that I'm going to show started as collaborations between the Spanish National Research Council, University of Malaga, and the Canadian National Research Council. And more recently, a few months ago, I also started a small spin-off called Alcyon Photonics to try to take all these ideas that we develop in the lab to the real world. So before I start, I hope you don't mind that I go off track for a little second, and I'm actually also working in the creation of the first national LGBT association in science and technology. So I believe that we as a community are underrepresented and invisibilized, and I also believe that there's a gender breach in our field that we should address. So in case you are interested in the association, or in case you want to discuss ways in your company or your institution could make a more inclusive environment, I will be more than happy to discuss everything later on after this session. So back to work. So basically, I'm going to present two different building blocks. One is a mode multiplexer, and the other one is a polarization beam splitter. And both of them are upgraded or enhanced by ways of sub-wavelength structures. So that's how we are going to start, in case you are not familiar with this subject. So basically, as Inigo has presented before, most photonic circuits actually rely on a very small set of building blocks. We work in the passive layer, so there is more flexibility there, but there are still very few items that you need, like couplers, splitters, multiplexers. So if you are using different Lego pieces to build your whole device, your chip cannot be better than the pieces that make it. So our question is, how can we make better building blocks? We have seen that there are many different options when you choose a material platform, but once you make your choice, you're limited to that particular material, that particular layers. So I work mainly in silicon photonics. So in silicon and insulator, what you have is a very high index contrast. That means that you can have very compact devices. But that also means that you have very high birefringence and that dispersion can be problematic too. So basically, when you design your device, your building block, you can choose where to put your silicon, but that's about it. So you're tied to that material. So we want to know if there is a way to be able to have more design flexibility without making fabrication more complex. And the solution is actually sub-wavelength gratings. So this technology is as simple as periodic structures where you have core and cladding slits. And the thing is, if you make this small enough, smaller than the wavelength of the guided light, your beam isn't going to see this as transition, but it's going to be to see this as a homogeneous medium that combines the characteristics of both the core and the cladding. So actually, before you only had two refractive index for your design, the core and the cladding, and now you have everything in between. because by choosing the amount of each one that it's in a single period, you can actually choose the refractive index in that particular area. So that's the first approach, and that's already a huge freedom when designing. But sub-wavelength gratings can do much more. Because when you play around with these geometrical parameters, you can actually not only change the refractive index, but also the dispersion of your material, leading to broadband applications. And more recently, we've discovered that you can also play with the anisotropy of it. So basically, this opens a whole new field for the development of high-performance building blocks. So I'm going to talk about two of them. The first one is ultra broadband mode multiplexer, which also are I'm also going to show a small sneak peek of the first experimental results of our spin-off company, so I'm really excited about this. So, well, of course, the concept is very clear. You have a single waveguide and you want to maximize the amount of information you can send through it. So one of the different options is to have different optical modes propagating through the same medium. So you have 3 channels of information that start off with the same mode type, and then you need a very fundamental building block, which is a mode multiplexer and converter. So you take each one of these channels and give it a different mode shape, so a mode order. So that way they can propagate through the same channel without interfering to each other. So this actually is quite a tricky building block to fabricate, or at least to fabricate with a broad bandwidth. There are several ways to go about it. You can do both stages separately. You can have either mode multiplexer on one side and mode converters on the other. But the more interesting approach is to have both effects in the same device. So these are some solutions in the state of the art. So you basically start introducing 2 T0 modes on 2 inputs, and then you somehow manage to one of them convert it into a T1 and join them together in the same output waveguide. So what is our solution to this problem? So this is what our mode multiplexer and the multiplexer looks like. So if we forget about the sub-wavelength part, let's think of this as a regular MMI. So this MMI, what it does is whatever comes from one input, it splits the power half and half, and there's also a 90-degree shift in one of the outputs. Then we have a 90-degree again phase shifter, and then we get both arms and put them together again. So let's start at this input. So if we get this mode here, then we have 50-50 power split, and the phase shift here is positive. So if we do a 90-degree phase shift in the opposite direction, what we do is we end up with both halves of the signal in phase. So when we get them together again, we are still going to have a T0 mode. However, if we start here, the phase shift changes. So the 90 degrees is here. So if we incorporate an additional 90 degrees phase shift, both halves will now have opposite phase. So when they get together in the same output waveguide, you will get a T1 mode. Okay? So this happens regardless of this having sub-wavelength or not. By the way, this is one of our patents, which was licensed to the company, and we're also getting very positive feedback from the Spanish OEPM. So let's imagine we have a conventional MMI with a continuous waveguides. So basically, This is all defined by the bit length, it's called, and it's the distance at which you have this power split condition. So you can design that for a given wavelength, but as soon as you move away to another wavelength, the position where you should be extracting the signal will change, and you will start getting losses and worse crosstalk. So that's where the dispersion engineering capabilities of sub-wavelength gratings comes along. If we make the whole MMI to be sub-wavelength, then we can have a very flat response to wavelength, which opens the way to having very broadband operation in the whole device. So just so you have an idea of how powerful this is, the dotted curves would be your response if you have a conventional MMI, and you see that, for example, if you design it for 1550, as soon as you go away, then you start getting more losses and a worse phase relation. However, as soon as you go to sub-wavelength, you can actually find a very optimal combination of geometrical parameters to have an extremely flat response, and this is over 300 nanometers, which is an incredible enhancement compared to our starting point. So this is a little tricky to design, but luckily we, and particularly people in Malaga, have a wide experience designing these kind of devices. So once we have this, the rest is quite easy. We just need to design the phase shifter, which in a first approximation is as simple as having different widths of the waveguide, so you can just optimize the geometrical parameters. There are more complex ways to do this, and we expect further improvement thanks to this. But this is pretty straightforward, and then you just have to design the angle of this E-splitter, so you don't have many losses when having both modes put together. So if you have all these three pieces put together and you simulate this using full 3D FTD simulation, this is actually the theoretical response of the whole device. So basically, we can get insertion losses under 1 dB in a range of 300 nanometers. So that covers all the communications band in the region with the single device. So you actually don't need to do any kind of redesign if you're only using partially, because it covers all of it. And we have crosstalks better than 20 dBs, again, in the whole device. And the overall footprint is still very small, because the MMI is very compact, which I didn't mention, but you can also make more compact devices using sub-wavelength gratings. So this is actually a really good example of how powerful sub-wavelength gratings can be. But what many people wonder when they see these kind of devices with all these small pieces is, what happens if you take this out of the simulator and you put it into the real world? Because intuitively, this looks like very hard to fabricate. But it actually is not. And this is the first chips we've ever fabricated in Alcyon Photonics. And in order to go to the sub-wavelength regime, we can work with periods of around 220 nanometers. This means that your slide is going to be 110 wide, which of course is small, but it's still very feasible with many commercial foundries. And this is all talking about 1550. As soon as you go to higher wavelengths, it also makes a more flexible minimum feature size. So again, this is what the whole device looks like. And we were quite excited to receive it and see that it actually works. So the first thing that we need to see before we characterize it in an objective manner, like I mean with numbers, is to see that the modes are actually being formed. So if we just put the device and we input light on the first port, what we should see at the outside is the T0 mode, which looks like this, just like a blot of light, which is what we expected. These are only preliminary results. We haven't been able to measure the full wavelength range that we are expecting it to work, but we see that even from 1495 to 1635, which is about a little less than 150 nanometers, we do get the mode formation that we expected. And the TE0 is the easy one, so we also get that with the T1. We get the two lobes of this mode, again, in all the wavelength range that we were able to measure in these preliminary results. These are only pictures, so we also need to know how good these are, like what are the actual losses and what's the actual crosstalk. So in order to do that, we put two devices back to back. So we have an input, we convert to the mode, and then we convert it back to the original mode. And these are the actual experimental results that we have gotten extremely recently. So in the range that we were able to measure, losses were in both cases under 0.7 dBs. So again, if our target to define the wavelength operation range is 1 dB, we are still expecting quite some more room on both sides. And then again, with the crosstalk, we are under 20 dBs in the whole range that we were able to measure, and we expect it still to be quite more. So for now, I can tell that the bandwidth is going to be over 145, which is already a good accomplishment, I think. But when we are done with the characterization, I hope this value to go up quite a bit. So this is the first device that I wanted to show. And the other one is a polarization beam splitter, which is also a key building block in many applications. People have proposed many solutions to this problem because it's something that affects almost any application. So you have directional couplers, you have MMIs, you can enhance this with sub-wavelength gratings. There are asymmetric MMIs, a lot of waveguides, plasmonic waveguides. And there are some very impressive solutions in the state of the art, but they also show some limitations in one way or another. So some typical ones are the bandwidth, the fabrication complexity, because whenever you start working with polarization, one thing that's very useful is to have different heights, different shapes, which is good for a laboratory, but it becomes tricky to do continuously, like in a commercial product. And also a big problem whenever you're working with polarization is the tolerance to fabrication errors. These kind of couplers are usually very sensitive to that. They have great performance, but if your width deviates a few nanometers, then things start going awry. So what we did is we took one of the more simple options, which don't usually have the best performance, and we tried to make it better. So let's look at the conventional MMI. So basically, the idea here is similar. So at one input of the MMI, you have the T mode and the TM mode, and you want to separate them. You want to have TM on one output and T on the other output. So this is schematically what happens within the MMI. So this is your input where you have a mode in a position, and then you have, it's called Talbot self-images at given positions, which are defined by the effective index of the waveguide within the MMI. So basically, at some lengths within the MMI, you're going to have the same mode on the opposite position. You're going to have the mode split into positions and then back again here. So, for example, you could extract the T mode at any position where you have it back here, whereas the T mode, whenever it's here, you can extract. So the challenge here is that you need both conditions to happen at the same distance. Otherwise, you only extract one of them. With conventional MMI, you can choose the parameters, but there's not much design room. There's not much flexibility. So there will, if you repeat this enough times, there will be some moment where both of these happen at the same time. But that's going to be very long devices. So how can we make them coincide at the same distance? This is what we would want. We would want the self-image at this position to be produced at the same position as when the T is at this position. Not my finest graphic design, but I hope you get the point. So if we want to do that, a first approach would be to use the kind of sub-wavelength MMIs that we've been shown. This gives you two more geometrical parameters to play with, which are the period and the duty cycle, which is how much of each material is within its cycle. So the problem is that this gives you more freedom on design, but whenever you change either the pitch or the duty cycle, it affects both polarizations. So again, it's not easy to achieve this condition that we were talking about. And the actual conditions where that happens tend to be in small pitches or uneven DC, which means that they are really hard to fabricate. But turns out that there's an additional geometric parameter that no one had been using, and that is the tilt angle, which was a very interesting innovation, because turns out that given a sub-wavelength structure, if you tilt it, if you make this in an angle, then it affects T polarization a lot, but it affects TM polarization in a very small manner. So this is actually in just a waveguide. This was published last year in a very nice paper. So as you can see, as you tilt your structure, the T mode drops sharply, and the TM mode increases a little, but in a very small magnitude. So this again opens a new field, because then you can work on both polarizations independently. We are using this for this kind of splitters, but this actually is very promising for many other polarization selective or polarization independent applications. So let's see how, if we take this idea that we demonstrated for just a waveguide and we apply it to the whole MMI, then we can play around a lot with the effective index that are seen by both polarizations. And we can actually match that condition that we were looking for in a very short space. So here in this propagation, you can see, for example, the T mode enters here, has a self-image here, and then forms again here. And the distance of the TM mode is exactly twice as much, which is a condition that was very hard to get with any other topology of the MMI. So we can actually make this power splitting in less than 100 microns. Maybe there's no need to go much in deep here, but it's interesting to know that we demonstrated this for two different SOI thicknesses, 220 and 260. Although we focus mainly on 220, we wanted to see the effect of other parameters, and we also wanted to know that it can be exported to other material platforms. So basically what we have here is this bit length, which is the position where you can extract the mode, for the TM mode and for 2 times the T mode. So you can see that for different angles, this is the tilt angle, the condition is verified at different wavelengths. So basically you just need to choose the tilt angle that's closest to your operating wavelength. So once we have this tilt value, we can just design everything around it. And this is our final design. So for the 2020 platform, we get an optimal tilt of 7 degrees. Again, we are working with the same period and pitch that we showed in the previous device, so it's actually very reasonable to fabricate, and we get less than 100 micron long MMI. So the full performance, if we look again at losses below 1 dB and extinction ratios over 20 dB, this is actually verified at a very broad bandwidth, over 130 nanometers. And if we focus on the central wavelength, the performance, of course, is even better. So again, these are very promising results. We are in the process of, as in the other case, taking that to the real world. So we have the first pictures of this device, but I'm afraid I don't have, we don't have still any measurements to show you. The first impression is that the losses look great. We'll see about everything else. We'll probably need to play around a little bit with the angles. But again, we're very optimistic about the whole device, and if it comes any close to the performance that we expect, it will be quite a success, I think. So basically, this is it. I hope I've shown you how sub-wavelength gratings can open up a new world of flexibility of design. And we work mostly with silicon on insulator, but the same concept can apply to any material platform. So I've shown you again the two-mode converter and multiplexer and polarization beam splitter, but this is just the beginning. So in case in your field, in your line of work, you have specific needs of building blocks that you don't find commercially, or like conventional solutions that don't have enough performance for your applications, then just come talk to us and we'll see if we can use this technology to offer better solutions. And that's about it. Thanks for your attention.
Thank you so much, Aitor, for the nice presentation. Is there any question? Any question? Well, in my case, I don't have any question because all the questions I had before are already response. So. Okay.
Hi, thanks for the nice talk. I would like to know, because you saw some demonstrations, what kind of lithography technique were you using to fabricate that?
It's conventional E-beam, so there's nothing very specific about it. Our goal was to, even though the design is more complex, to have a solution that's easy to fabricate in any commercial foundries. So that's why we stick to minimum feature sizes that can be fabricated with conventional technologies.
So my second question, I have a second question. What is more or less this minimum feature size you require for these devices?
In this case, for 1550, we tend to work with minimum feature sizes of 110 nanometers, which is achievable in most cases. If the fabrication method still has problems with that, we can still push it a little farther. We are still far from the Bragg regime, so we can still play around with that.
Thank you.
So, any other question? Okay.
Very nice presentation. Can you elaborate on what's the angle effect that you have on this polarization device that you presented?
Yes. So basically, if you want further information, I would recommend to look into this paper because it's very nice about explanation. But the thing here is that yeah, basically the T mode are greatly affected by it. You can see here we did tilted waveguides from 0 to 45 degrees, and we see that we can go from an effective index of 2.2 to down to 1.8, which is a 0.4 range where you can design, which is quite a broad range, just by changing that. And in that whole range, the T mode is affected by less than 0.1. So basically, you can make your design with straight non-tilted waveguides for the TM mode, and it's going to be unaffected. And then once you have this first approximation of your solution, you start tilting your structure to change how the T mode operates. Of course, this is when you have just a monomode waveguide, it's a very simple approximation. When you start having a whole device, the effects aren't as intuitive. They are in the same magnitude, but you do need quite an extensive simulation work to see how it affects your particular device. Here, however, you can see here how the angle affects the pitch length. So basically, as you start tilting it more, you will be pushing your images farther away. So yeah, that's why it's going up. And see how it's also very clear here that these horizontal lines are quite separated, whereas the effect on the dotted line is quite small. No.
Okay, so first of all, excellent presentation, and I think impressive results. The loss results you showed in the beginning is like 10 times smaller than I would have been expecting before you showed them. So that was really impressive. What about the stitching in the EBL, and kind of is this sensitive to the stitching? So basically, if you are using multiple kind of windows in the EBL to do the writing of this, so is it sensitive if you have somewhere like a small shift, or is the sub-wavelength grating actually insensitive to that, or not?
Actually, since you have more degrees of freedom, you can actually find solutions that are less sensitive to fabrication errors than other conventional technologies. And I'm not sure I can give you the exact values, but we did some extensive simulation on this one device, and we did get we ended up choosing some geometrical parameters that maybe aren't as optimal for bandwidth, but that are more resilient. And I think I have a terrible memory with numbers, but basically we were able to go like 5–10% changes in the duty cycle and still maintain a bandwidth with very little degradation.
Okay, I think there is no more time for questions, so let's send the speaker again.
Thank you.
Okay, thanks all for attending this session. In the next 1 hour and a half, we still have a set of B2B meetings. Sergio is showing again the table with the allocated meetings. For those that are not in the meetings, there are 2 possible visits planned. Well, there is a third one that you can go to the beach and come back later, but stay in the university if you want to visit our Photonic IC labs, or you want to get to know something more about our clean room. We're going to be having 2 visits for each, one at 6 and one at 6:45. So please come by the registration desk and join us if you wish.
Okay, here you are the next block of B2B meetings. It's now at 6 o'clock. We have five meetings. Then at 6:30 we have 4 more meetings. But anyway, we have halls here, and at 7 o'clock too. Then if any one of you want to want to have another meeting, please come with me, and let's go. 30 minutes for each meeting, and time goes. Okay.